Ladies and gentlemen, good morning. I'm He Tingbo from Huawei. And it is my honor to attend the ISCAS 2026 and deliver today's opening speech. Over the past 6 years, I have often been asked, in industry as competitive as mobile and AI, how did you survive and come back to the top? First, I want to thank our customers and partners for their patience and support. During the 6 years, my team and I have explored new paths in semiconductor and found a way for sustainable evolution. Today, based on Huawei's practice, I will share what we have done, what we have thought, and what we have learned. For decades, the booming semiconductor industry has propelled human society into the information era. Behind this miracle is Moore's law, a principle with both technical intuition and economic significance. Moore's law was historically very promising, delivering performance while staying cost-effective. Every year, we got more powerful devices, better smartphones, personal computers, and more advanced AI systems. But this evolution relied heavily on geometric scaling, which began to slow down. Well, FinFET extended the roadmap for another decade. Beyond the 7-nanometer node, we and our peers met serious challenges. Geometric scaling needs the most advanced leap arrived earlier and more tougher. So, semiconductor evolution is more than geometric scaling. Geometric scaling itself has always delivered time domain gain. Faster transistors, shorter response time, higher chip frequencies. This means space and time are two sides of the same coin. Losing geometric scaling does not mean losing time scaling. So we proposed a shift from geometric to the time scaling as the new guiding principle for electronic system evolution. We saw time scaling can deliver strong benefits across devices, circuits, chips, and systems. Time scaling is the ultimate goal that the system evolution has been pursued. Continuously raising operating frequency for higher performance. At the device level, is it really hard to shift to time scaling? Quite the opposite. A device's typical operating time is at the picosecond or nanosecond level. Even without geometric shrinking, we can gain performance through the front end and the back end RC optimization, because tau itself equals RC product. Examples such as high-K metal gate, strained silicon, those very good technologies are successfully introduced to the past nodes. They all can improve the device performance. So from device to circuits and the chip, evolution can be centered around the time, from picosecond to nanosecond to second. In total, 12 orders of magnitude. At the circuit level, signal propagation time is linked to interconnector RC parasitics, pipeline length, and the circuit depth. At the system level, architectural innovation and system optimization dominate, enabled by device and the process improvement. Using time as the optimization target for the entire electronic system, it is more comprehensive, more consistent, and more seamless. Let me show you what the time scaling meant in our products. Let's start with the mobile. For a smartphone, one chip forms the entire system. So we must work across device, circuits, and the chip levels. After 2020, together with our partners, it took a huge effort to bring our mobile chip back to the market. Extensive DTCO and STCO core optimization works deliver pleasing results for our mobile customers. But by general expectation, after Kirin 1930 Pro launched last year, our chip may have reached saturation. It will be very challenging to maintain the same momentum of evolution. But this is also why I'm here to have the speech. Have we run out of surprise, or are things about to change? Under the Tau-centric guideline, we found the new path. This year, we a surprise for the whole industry. In fall, winter 2026, we will bring the surprise. Not saturation, not continuation, but a big leap ahead. So how did we achieve this breakthrough within the saturation zone? When a single die reaches its limits, multi-die approaches naturally come into play. We have adopted this technology widely. But the inter-die interconnection deserves a close look. The typical interconnector pitch has evolved from hundreds of microns for BGA boards to around 100 microns for bumpings and 50 to 25 microns for micro bumps. Also about 10 microns for hybrid bonding. We see this play across HBM3 to HBM5, shifted from a micro bump to a hybrid bonding. These technologies, including HBM, 3D V-Cache, and others in the industry, improve bandwidth and reduce latency. Those very good technology or products, along with Tau scaling. But for Kirin, well, one chip is the entire system. They are not enough. We have to take steps forward. So, what we did for Kirin? Back to the tau scaling process. We found the breakthrough. We name it the logical folding. Let me first give a clear definition. Following the time scaling principle, logical folding is a new but universal design methodology for digital circuits and systems. Synthesizing digital systems across vertical stacked active tiers. Logical folding optimizes the power, performance, density, and cost jointly and constantly. With this definition in mind, let me introduce how it works. Simply speaking, digital circuits split into combinational for Boolean logic with no state, and sequential with flip-flops to hold the state. Primary timescale is to reduce the logical depth of circuit paths between flip-flop stages. In the backend, placement and routing work must balance the clock tree and minimize critical path delay. Therefore, critical path timing is the governor metric of digital system performance. For circuit design, logical folding aggressively compressed propagation time between adjacent flip-flops. By distributing critical path gates across different planes, we shorten signal wiring and lower parasitic RC. Clock variation drops sharply. Reserve margins are largely eliminated. The critical path tightens and the chip runs faster. To enable effective logical folding with free logic design, we need a very, very aggressive bonding pitch and fan-out ratio, or the gear ratio of the metal stack. Through many trials, we found the ratio of hybrid bonding pitch to the top metal pitch should be less than 3. That would be good, very good. In other words, we know that the top metal nowadays is 720 nanometer. That means the hybrid bonding pitch itself should be smaller than 2 micron. At this very moment, the logical folding miracle occurs. Kirin 2026 is here. Going to market later this year, it marks our first ever successful implementation of logical folding. It is built on a brand new free logic design concept, expanding from a single layer to a double layer architecture. Before logical folding, it took 3 years to lift the transistor density from 126 to 155 million transistors per square millimeter. That's in fabrication perspective view. In 2026, logical folding take it all the way to 238 million transistors per square millimeter in one single step. At the same time, the SoC performance core power efficiency improved 41%, and the maximum clock frequency increased by nearly 13%. To realize logical folding, together with partners, we drove a wave of innovation at the device and the process levels. The hybrid bonding, the pitch is now sub 2 micron. Actually, it's 1.5 micron. The alignment overlay error under 0.5 micron. And with smart redundancy, the yield reached 100%. For TSV, the critical dimension and keep-out zone scales down to sub 1.5 micron. Pitch sub 6 micron, the failure rate below 100 parts per million, and the repair rate reached 99.9%. The technical journey continues. We are developing low-temperature hybrid bonding to optimize thermal budget and moving TSV landing from the top metal down to the metal 6 or metal 5, freeing more than 30% of high-level metal routing resources. These innovations may be not all onto mass production this year, but will introduce to the mass product from this year and beyond. Going further along tau scaling, we redesigned several critical circuits. From the high-performance computing chips in the data bus, we built a high-speed global network of chip bus using top metal layers on both up and lower dies, shorten the transmission and more stable power delivery, cut the data path footprint by over 60%. Also, for the clock path, innovative architecture enables the post-silicon clock scheme adjustment, contribute over 5% SoC performance improvement at its own for this design. This page, I will use SRAM, another example to further explain circuit folding. SRAM performance depends not only on transistors. Access speed, per bit energy, and area efficiency depend strongly on interconnect lengths, such as bit lines and word lines, as well as the communication delay between bit cell array and peripherals. As area size grows, interconnector and communication delay dominate over the transistor intrinsic delay. For a 1 megabit SRAM today, they account for over 70% of total latency. We apply the logical folding to SRAM. First, folding shortens the critical path by reduce the distance between bit cell array, peripheral circuits, and the processing cores. Second, we optimize the RC of each SRAM component. Overall, SRAM access latency reduced. energy per bit dropped, and the operating frequency rose by over 40%. This is a huge number, especially for SRAM. It's really very hard to achieve this in advanced node. More things. Logical folding brings benefits for processing cores, especially for clock tree performance. For this processing core, by shifting to double-layer folding architecture, clock buffer count dropped by more than 50%. We know each buffer, at least 4 transistors. And the clock skew down by 25%. That's so friendly for the digital system. And the wire length by around 30%. They also very hard to achieve in the advanced processing node. After 6 years, we established a preliminary methodology and a tool chain for logical folding. For Kirin 2026, we only applied a modest folding on key paths. The pitch of hybrid bonding only reached 1.5 micron, and next year it will reach 1 micron. And the landing level has only taken its first step. Even so, CPU performance core frequency will reach. This just the start. It took us 6 years to prepare many things, like EDA tools, design methodologies. I used to think that it may take us 10 years, but 6 years, we are here. In the next 10 years, we will move from local critical path folding to full scale and multi-layer folding. For full stack optimization from devices to systems. From 2026 to 2035, as a wide range of R&D exploration goes into the product, the transistor density will rise. Operating frequency will surge. And we keep delivering cutting-edge mobile chips to the market. Our solution is feasible and affordable. The performance of a new chip can fully compete with that of other parts. This is just the start, and it's a tall story so far for our mobile application. One might ask, and it's a fair question, can tau scaling, which works in the mini-watt smartphone world, also work in the gigawatt world of AI data centers? AI training and inference are highly parallel. Unlike mobile, AI is not about a single chip. Formed by hundreds of thousands of chips, AI system is ultra-large scale and highly parallel. In 1 decade, aggregator computing power at this scale has climbed millions of times. Our AI works takes shape at the supernode line, last year, Ascend 910C opened the supernode era. This year, Ascend 950 takes the gain to another level. Before 2030, we are using many technologies that the whole industry is using, such as chiplet, 2.5 dimension fan-out, 3D stacking by microbump, and normal-size hybrid bonding. Also, slightly, we will use some logical folding skills. But around 2030, we will launch new Ascend, the full logical folding version with another performance boost. The concept behind Ascend is still tau scaling. Let me explain how we apply the time-centric tau principle to enable powerful AI systems. AI workloads come in two shapes: large-scale training and inference. Two things are clear. First, networks keep growing from one chip to dozens, hundreds, even thousands. Second, look at the bill of energy and the bill of materials. Over 80% of energy goes into moving data, and over 70% of cost into storing it. Even more these days, to storing the data, yeah, even more. So, for both training and inference, the win is not just in shortening computer time. It is in shortening the time that the data spends moving between chips and inside a chip. In hardware terms, interconnector of inter-chip, memory bandwidth for intra-chip, and the raw compute for computation. These three kinds of times. For training, the design space is relatively wide. What we care about first is the throughput. The art is to overlap those three kinds of times, so communication level becomes the bottleneck. Latency is not the most important thing here. That's for training system. Inference, different. Inference puts more emphasis on faster response. Each job is much smaller, but must answer in real time, demanding both throughput and low latency. When we talk to AI, tokens must come back instantly, as soon as possible. The sooner the better. So tokens per second is what we chase. That is why currently we design two kinds of systems, each tuned its own tau. For the inference supernode on the right, by jointly optimizing the interconnector, memory bandwidth, and the compute, each generation moves the needle. When we shift from a single chip to the entire system, communication time becomes critical. Traditional computing is confined inside an iron box, and once outside, interconnector capability drops quickly. What happens when tens of thousands of AI chips work together? We need communication as strong as inside a single iron box. To reduce system time, we introduce a brand new bus protocol unified bus, or UB. In traditional multi-node, multi-AI chip architecture, data exchange often requires complex and redundant protocol conversions. Higher many protocols here. Legacy. High latency, low reliability, and high cost. UB unifies interconnect across the entire computer system. The same protocol and hardware used inside and outside the box. Through a fully peer-to-peer architecture, we avoid cross-layer conversion latency with improved reliability and reduced cost. From multiple protocols to one, UB makes large-scale AI system deployment much simpler. One of UB's new features is memory semantics. In the past, cross-layer data transfer must be encapsulated to the application layer, and then go through complex cross-protocol conversions. With UB, we achieve conversion-free, peer-to-peer transmission at the memory semantics layer, significantly reducing memory access latency. This is especially important for ultra-large-scale parallel systems. Through the fully peer-to-peer UB fabric, we have realized the system as one chip with very low latency, a unique tau system. Another story, also very important. Optical interconnector is another key technology we developed for AI. Packing more chips into one single rack pushes power density and reliability past its limits. All the engineers are mad. Recently, there are a few bad news from some very famous chips, famous in a company and their famous chips. Bad news, All this bad news, I think that by this reason. So for our tau systems, we choose a distributed computer across racks. And high one is a key enabler. 400 gigabit per second per AI chip is easily achieved by electrical cables. So for older generation chips, there are not so many bad news, because at that speed, those electrical cables are really reliable. But scaling to multi-terabit per second, cable becomes very challenging. SerDes reach shortens, cable grow bulky, and we cannot even attach panels for installation. Also, the power and thermal stuff become worse. To address these issues, we developed a higher density optical engine, High One. A single High One is here. A single High One delivers 8 terabit, matching the unified bus bandwidth for one AI chip. It shrinks the SerDes reach from 100 centimeter to 5 centimeter, or 40 inches to 2 inches. Eliminates bulky cables good for AI system deployment, also friendly for the power and the thermal stuff. Huawei also extends reach from under a meter to 100 meters, making high density in the connector for spread out. Gigawatt data centers of physical reality. Every memory signal, every interconnector signal, and every ampere of supplied current must cross the logic dice edge to reach the computer circuit inside. As the chip grows and more transistors inside, the edge gets more congested. If the chip has a set length n, compute power scale as n squared. But the memory bandwidth, interconnector, and the power delivery all carried by 2.5 dimension fan out along the edge, only scale as n. The widening gap between these quadratic and linear curves is the fan-out dilemma that stores 2.5 dimension scaling. System folding breaks this dilemma. By moving power delivery, high-speed memory, and optical I/O into the vertical direction onto surface instead of around the edges. All of this scale quadratically, matching the n-square pace of compute. We also heard a lot of very good technologies like backside PDN or on-face integrated SRAM or DRAM memories. Those work also because of this reason. Also this kind of trial. Also because of the scaling dilemma. So we think this is the path for the next 10 years. And it is already underway. Along the tall scaling path, we expect to increase the hardware integration by more than 100 times by 2035. Last but not least, for high-performance computer systems, memory and logic are not separate domains. They are two sides of the same coin. In the 8086 era, the industry decoupled processors and memories through standardized memory buses, memory I/Os. That separation enabled both industry to scale independently. Processor performance advanced rapidly and for different applications, while memory vendors grew alongside the expanding of the computer market. The AI era is now reversing that trend. Exploding computer density is pushing memory bandwidth, latency, power, and packaging to their limits, forcing logic and memory into ever tighter integration through technologies such as HBM and 3D packaging and so on. We call it 3D folding something. As the data movement becomes as critical as computation itself, the balance of inference is more and more shifting toward the memory sectors. Nowadays we see that. However, for the whole industry, lasting success will belong to those who can fuse logic and memory And just as important, build an economical partnership that allows both memory and processor, both industry, to share the benefits of the fusion over the long term. After all this practice, we know many challenges remain. First, folding needs new design methodologies and tool chains. Traditional tools are not yet sufficient for full-scale free logic design. We have done preliminary development with useful results, and the details will be released and published over the coming months. You may also find more information during our industry forum tomorrow afternoon. We warmly welcome partners and experts in this field to join us for future improvements. Secondly, thermal management is another major challenge. Chip power, especially thermal design power, keeps growth each year. The thermal pressure spans devices, circuits, chips, and systems. Also, 12 orders of magnitude, from milliwatt to gigawatt. We can identify the key issues at every level. To address transient current, we developed high-density integrated capacitors. At the chip interface, we need to control and optimize thermal resistance and conductions and so on. Looking ahead, we would like to work with industry peers and partners on energy efficiency and thermal challenges along the roadmap. The roadmap ahead is a challenge for the next 10 years, but direction is clear and resolute. 6 years along the tall scaling path, practice has delivered excellent results. At the circuit level, transistor density at the fabrication standard has climbed from 150 toward 240, even 300 million transistors per square millimeter, and approaching 400 million transistors per millimeter square rapidly. For SoC design, effective transistor density climbed from under 100 to more than 250 million transistors per square millimeter. Sustainable density improvement is now within reach, and the tall scaling opens a new design space. CPU performance core is to go in beyond 5 gigahertz by 2031. Logic folding holds circuit level efficiency at ISO power with deep hardware software core optimization. Kirin SoC efficiency will more than double in 3 to 5 years under typical DOU. At the system level, for AI system, we remain equally confident in delivering high quality, low latency, ultra large scale solutions. Through practice, we have proved that the tau scaling path is feasible, universal, and sustainable. At different time levels, we can define tau function as targets to optimize at each level and across the entire system. Here. Six years, 381 chips, serving different industry sectors and markets and customers. Our vision is to bring digital to every person, home, and organization for a fully connected, intelligent world. This remains our world.